Okay. We're going to finish talking about muscles today, and then we're going to start talking about resistance training. This is going to be pretty quick. A lot of the stuff in this set of slides is kind of very straightforward, fact-based kinds of things. It's covered pretty well in the book. So I'm going to hit a couple of high points on things and then tell you guys we're just going to move on, because most of you really don't give a shit about this, but you're probably going to be really excited about resistance training, which is the next thing that we're going to cover. I apologize, I didn't get the resistance training slides up until yesterday. I still don't have the lecture outline for it. I will get it up today. It's just been one of those weeks where I'm a little bit behind on everything. Okay. So what we're going to talk about to start is something called sensory motor integration. Okay. Sensory motor integration. So the show of hands. How many of you have ever touched something that was either hot or cold unexpected? Okay. Just about everybody. How many of you have in the dark stepped on a Lego? Okay. All right. Some questions for you guys. Maybe you have little brothers or sisters or various other things on all of that. Okay. What's the normal response? I touch something, it's unexpectedly hot or it's unexpectedly cold. Jerry's like, pull it back, right? It's got to pull it away. Okay. That phenomenon is, at its most basic, that is sensory motor integration. Okay. We have an ability, we're not going to talk about it very much, just very, very surface level kinds of things, of a part of our nervous system that brings information about hot, cold, okay, light or dark, different chemical environments, pressure in from the external sort of environment into our body, right? And a lot of that information is going to come from hands, feet, skin, places where there's going to be muscle. And what we're going to see basically is that those receptors come in, they're going to bring our information to the brain, and there are these close connections both in the brain and in the spinal cord where having sensory information can modify, or in some instances, immediately initiate muscle contractions. Okay. And so that is the idea of sensory motor integration. If I ask all of you guys to put your arm out, please don't. You'll whack your neighbor in the head. But like, you know where your arm is in space, right? You know where it is. And you know, oh, this one's going up, right? We all have that subtle, I lean to stay on balance. That's sensory motor integration. Okay. You perceive where your arm is in space, and then you perceive that that is changing your balance. And so you immediately change muscle contractions and things to move yourself to stay back on balance. Okay. That's this idea. That's the idea of sensory motor integration. No, I don't need subtitles. Okay. We're going to start with a little bit of information about the brain. Okay. And I just want you to know kind of the very surface level of all of this. This is not psych class. This is not anatomy class. We're not going to dive really, really deeply into all of the different things that are going to be here. Here's an actual sort of brain cross section. I like this one because it at least sort of has these bright colors and can begin to kind of differentiate in some ways the different areas that we're going to want to talk about. Okay. And so what we have then is the cerebrum, which is going to have our conscious awareness of stimuli. This is the place where we control movement, so it's going to include the primary motor cortex, right? You think most of your thoughts, cognition, and things are going to originate in the cerebrum. Okay. We have what's called the diencephalon, which is a regulatory place. It has the thalamus and the hypothalamus. So lots of hormones or neurotransmitters are going to be sort of produced here. We integrate sensory information in the thalamus and then the hypothalamus, right? with all of its different hormones and things that it releases, plays a really, really big role in maintaining homeostasis. Okay, so here, diencephalon down here, thalamus, hypothalamus, those areas there. We have the cerebellum, which helps us to control motor control. Okay, cerebellum down here, this kind of area right here in the back. Okay, and then we have the brainstem, which is going to be from this part that's going to lead on down into the spinal cord. Brainstem has automatic control centers. Okay, for respiration and the cardiovascular centers, which are still going to get regulated through the thalamus in some ways. Okay. And then a lot of the stuff that's going to go in, which is part of our sensory stuff, that is going to be kind of our perceptions of pain and our endogenous or internal ability to kind of ramp down painful signals, which we could spend an entire class talking about, that analgesia system. A lot of that is going to be kind of regulated down here, okay, through the pons, through the medulla, and some other specific structures that are beyond what we have. Okay. So I do want you to know just kind of the basic functions of these sorts of brain areas like this. Okay. If we break down the cerebrum, okay, we can look at things here in purple in the frontal lobe. This is where the primary motor cortex is. This is where we think of kind of the thinking part of the brain. Okay, is the frontal lobe. We have the temporal lobe, okay, which tends to be over on the side. Just going to be where we bring in auditory information, so stuff here. The parietal lobe is going to have sensory input, and then occipital is back here. Okay, parietal is more sort of back like this. Other sensory input comes in there. The occipital lobe in the back. You want to do a fun thing, hit yourself in the back of the head like that, and you'll blink and lose vision for just a minute. I had a super fun time with my occipital lobe yesterday. I'm blind as a bat. It was my yearly optometrist checkup. I have to get bifocals now. If you really want to feel old, you're like, great, and fucking bifocals. And of course, my optometrist was like, these are hard to get used to. I'm like, great, you're really giving me the hard sell here on all of this. But I find myself, I take my glasses off all the time to look at my phone and things. Like I really am a grandparent. But they had to they dilate my pupils to look around in there and make sure everything was okay. And so it was all kinds of jacked up. Ellis had a big fun with me later today because I had these fun, little roll-on sunglasses that you wear under all of this when they sent me home with everything. So she was putting them on her. She liked them so much. She was putting them on one of her teddy bears and everything. So anyway, occipital lobe vision. That's where stuff is gonna come in. Okay. What we are really going to be concerned about, okay, from a sensory motor integration standpoint, is where the primary motor cortex is here in the frontal lobe, and then the integration of all of our signals that are going to come back and kind of be organized and processed in the parietal lobe back here. Okay, so they're reasonably close to each other, but there's going to be neuronal connections between this information in the parietal lobe and the primary motor cortex in the frontal lobe. So as we're doing motor output from here, we get information about our environment, it gets organized and kind of put together here in the parietal lobe, and then that information can then be directly transmitted over here to help us make any kind of appropriate adjustments in how much force or which muscles are on and which muscles are off, right? Like I touch this thing, it's hot, pull away, move away, am I off balance or not? Things of that nature. Okay. So in the peripheral nervous system, all right, we've been covering brain stuff that's central in the peripheral nervous system. So out in your arms and your legs and places like that. Okay. We've spent a lot of time already talking about the motor division. So alpha motor neurons, their axons, right? The neuromuscular junction where it synapses out onto the muscle. How we're communicating in some ways top down, brain out to muscles. But there is conversely the sensory division where we have receptors in muscles and skin around blood vessels and things, but they're going to signal through what we call afferent nerve fibers. So there's a receptor in your skin and it perceives touch or pressure. Okay. And so what's happening is everybody take your finger and just like tap on your forearm a little bit, right? You can feel it, right? Most of you can feel that. Okay, if you do that, now press a little bit harder, you can feel that the pressure is going up, and at some point, you press hard enough and it's painful. It actually hurts a little bit, okay? What happens is there are receptors here. That pressure activates those receptors, and then those receptors have their own axons that are gonna run essentially the opposite direction of stuff coming out that leads to muscles. So they're gonna go from here back into the spinal cord. Okay, we call those receptors and their axons afferent nerve fibers, okay, or afferent nerve fibers. Afferent brings stuff from the periphery back in. Efferent is what we've already been talking about, our motor axons. Efferent go from in to out, okay? But the interesting thing about these two things is, let's just say in my forearm, okay, the afferent fibers that are in my forearm go to the spinal cord and they go in on the opposite side, but at the same location as the efferent motor neurons and their axons that actually go and tell that muscle to contract. So sensory information is brought into the spinal cord at the same level as efferent information that goes out to tell those muscles to contract. So they're right there together. Okay, that's going to become important in just a couple of slides. Okay, we get sensory input from pretty much every tissue. Okay, you ever had an upset stomach? You ever had a tummy ache? Right. If you have, how do you know that you're having a tummy ache? Right. Fibers. You have afferent nerve fibers there that tell you something feels wrong. Okay. In many ways, the only kinds of tissues that we have that don't have a lot of that signal are your brain and your heart. Okay. Brain and your heart. So when you have a heart attack, you have to borrow the fibers from the surrounding tissues to be able to generate signals in those ways. But we have most internal organs, lots in connective tissue, lots in and around blood vessels, a ton in your skin, and some in your muscles. So we're getting input about the environment in those cells and around those locations, as well as things coming in from our external environment. I do want you to know the types of receptors, okay? We have things that sense touch or pressure or stretch are called mechanoreceptors. We have what are called thermoreceptors. You want to guess what a thermoreceptor perceives? You all should have said, right, light or something. No, it's temperature, of course. Chemoreceptors that are going to tell us things about the internal biochemical environment in and around a cell. They sense things like hydrogen, so pH or acidity, potassium, lactate, ADP, inorganic phosphate. These are going to be really important for regulating metabolism and things that we're going to get into next. We have things that are called nociceptors, and then things that are called photoreceptors that sense light. I should make a comment about the nociceptors that generally the XPhys book doesn't talk about nociceptors correctly. Essentially, all of these other kinds of receptors, if they get a large enough stimulus, are nociceptors, right? If nociceptors sense pain, well, they're very specific, and I have a photoreceptor that senses light, and if it gets activated enough, then that light becomes painful, right? Or if I get enough of an increase or a decrease in temperature, that temperature change becomes painful. So we don't have things that are very, like just a non-specific pain receptor. It's usually all of these other kinds. Okay. All right. So let's talk about two very specific kinds of things that are going to go on in muscles that are going to help us understand sensory motor integration a little bit better. Okay. So a lot of the information that we get from muscles is also going to come from the joints around that particular muscle. And so we need, in order to prevent injuries and to maintain force production and modulate force production, we need an ability to figure out where are we in space, okay? and what is the relative amount of force and stretch in a muscle or around a joint. Okay. And so we are going to sense this through a couple of things in the muscles and the joints, and then what we're going to call kind of free nerve ending receptors that are just kind of random things that are out. Okay. So in a muscle, we have special muscle fibers called a muscle spindle. Okay. Called a muscle spindle. They sense stretch. Okay. They sense stretch. Can you guys all see me down here? I'm very nervous now. You're looking at me in the midst of all that, which I know is an odd thing, right? Like I teach and I have to stand up here and you guys look at me and I'm deathly afraid of that people are paying attention to me. It's a very strange phenomenon, but okay. See guys what I'm doing? It's a reflex, right? This is the tendon tap reflex. That reflex, I am activating muscle spindles. They are sensing as you stretch the tendon that it changes the length of the fibers that tendon connects to in your muscle, and it evokes a reflex. But we'll talk about a reflex, but that's driven by a muscle spindle. Okay, we have a thing called the Golgi tendon organ, which is going to be right where the muscle first connects to the tendon, and it monitors not length but force. Okay. I've always thought like those things are backwards. I thought the thing in the muscle should sense force and the thing in the tendon should sense stretch, but that's not how it goes. They sense force. Okay. Golgi tendons in a lot of ways set an upper limit. Okay. They set an upper limit on everybody. If you get to this much force, it stimulates the Golgi tendon and then it tells the muscle stop. Too much force. We're going to rip the tendon. We're going to rip the muscle in half, shut it down. Okay. Shut it down. So that's the job of the Golgi tendon. We have what are called kinesthetic receptors, which a lot of times exist in our joints, and they're going to give us just a sense of position, right? Some kinesthetic receptors are going to connect directly into, they're going to signal to the brain, and they're going to augment breathing. If you start moving at all, your breathing goes up immediately. All you got to do is this, and breathing rate goes up. It's directly connected to these kinesthetic receptors. And then we have free nerve endings in muscles that sense pressure, temperature, right, the chemical environment, and are going to give us some information that we may or may not pay attention to as it relates to continuing to generate force or to monitor and augment force production. Okay. So that's kind of joint muscle sensory perceptions here. Okay. Now, do you guys talk about spindles in anatomy or in human frizz? Y'all talk about those a little bit? Some of y'all are like, fuck no. Okay, did not. All right. So muscle spindles, if I cut open your muscle, you have some fibers. We can't identify them just by looking at them. We got to do a couple of other things, but you have what look like regular muscle fibers, but they're actually not. They are muscle spindle fibers. And spindles are a mechanoreceptor because they sense changes in the length, this mechanical deformation. So here's our muscle. We have our regular fibers, and then we have our spindle fibers, and they look like a regular fiber, and then they've got these nerves wrapped specifically around them. Okay. And so they are actually a collection of several little fibers. We call them intrafusal fibers. Spindles are intrafusal, regular skeletal muscles, what's called extrafusal. I'm not going to ask you about that, but they're going to be interspersed at regular intervals all the way through your muscle. Okay. And they're interesting because they have these nerves that wrap around them, and they are going to have a capacity to sense changes in length, so they can function from a sensory standpoint, but they also have their own unique motor innervation. Spindles are innervated by something called a gamma motor neuron. And so what this lets them do is you go and you stretch, it senses the stretch, so it sends the signal to the central nervous system, ooh, we're stretching. But then you can use the gamma motor neurons to change the length of the spindle, and essentially turn the volume up or turn the volume down on how it senses stretch in that way. Okay? And so what, by doing all of this, we can make it more or less sensitive to an amount of stretch. So it's like, okay, I'm stretching, I'm stretching, I'm stretching. It sensed it and it's like, okay, we're stretching, we're okay. Go ahead and turn down how sensitive we are to a change in weight. Right, so we have an ability to kind of reset that. So here's how spindles work. Right? Spindles send a signal. You stretch a muscle, spindle gets turned on, and it signals back to the spinal cord via its afferent axon. Okay? The spindle will have a direct synapse on something called the homonymous motor neuron. Okay? What this means, homonymous just means same. So we've got a muscle out here, right? Everybody can very clearly see that's a muscle. Here we have the spinal cord, and we've got alpha motor neurons here that have an axon that run out like this. The spindle fibers are going to send back, and they're going to come in on the other side. And so this is, we'll call this the spindle. And they synapse directly on the motor neurons that are going to that muscle. Okay? And what a spindle does is as you start to stretch, what it wants to do is to think, ooh, stretching's bad. Okay? Stretching could lead to overstretching, which could lead to tearing the muscle or the tendon. So when the spindle gets activated, it signals back here and says, hey, alpha motor neurons, give us more force. Okay? Let's do more force so that we don't stretch as much. Let's try to shorten that muscle. Okay. We also then, we can have, right, so this is the agonist muscle, right? This is, let's just say my bicep. And then over here, I have an antagonist, right? And it's got its alpha motor neurons there. And the spindle is going to actually signal to both. Okay. So the spindle tells the muscle that's being stretched to generate more force. It tells the muscle that opposes the agonist or the antagonist to relax and shut down. So I'm doing a curl and I can't get it kept up. I'm trying to curl. Nope, it's not working. It's going back down in that way. The spindle senses that stretch and says, hey, bicep, give us more force. Tricep, turn off, right? Because the tricep could be preventing us from applying all of that force. And that's how the spindle reflex works. Okay. So when I sit and I do the tendon tap, okay, the reason I get knee extension is stretch in the knee extensors. Spindle gets activated and says, fire the knee extensors. Hamstrings shut off. Okay. So we do this and I get knee extension. Okay. Does that make sense, guys? Yes, no, maybe. Do we need to do some squats and feel ourselves sort of lengthen our muscles and change our perceptions of everything? No. Matt's like, no, none of that. You sure?
No, like this, but
Okay. All right. That's how the spindle works. The Golgi essentially does the opposite. Okay. It essentially does the opposite. It perceives force, but when it gets activated, the Golgi turns off the homonymous motor neurons and activates the antagonist motor neuron. So I'm doing a squat, okay? Make y'all do these too, but I'm doing a squat. As I go down, one, I'm getting stretched, that's fine. I'm coming back up. Big amounts of force, okay? Activate the Golgi tendon. So I'm trying to do a squat, Golgi gets activated, and it says turn off your quads, right? Turn on the hamstrings because it thinks there's too much force. Put this weight down, stop doing this. Okay? Protect from high force level. So the Golgi do in the opposite. Okay? It's going to tell homonymous off, antagonist on, whereas the spindle is homonymous on, antagonist off. But both of them serve to prevent overstretching and the application of too much force. They're trying to protect our muscles and our tendons. I thought there was a question. Somebody had a question over here? No? Okay. The fun thing is you can train your Golgi tendons to not be so sensitive. Okay. And it's like, what? All you got to do is go and get a heavy weight, pick it up, and stand there with it. Get in the squat rack, unrack the weight, and just stand there. You don't have to move and do anything. Just stand there with the heavy weight. And it will, in some ways, if you do that over multiple days and weeks, it essentially reprograms the Golgi tendon, because the things we held the heavy weight, nothing bad happened. We're cool, right? Don't be that sensitive to it. I can make every one of you stronger just by having you essentially unrack and hold the weight, by turning down the sensitivity of your Golgi tendon. I've not actually made your muscles bigger or anything else. All I've done is allow you to reach more of the potential based upon the amount of muscle that you actually have. Okay? So this is one of the things that we think plays a role, as you guys will see probably on Friday, in how strength goes up with resistance training. Is part of it is your muscles get bigger, but then another part is that we just turn down Golgi tendon sensitivity. Okay. Okay. We'll kind of finish off really quickly here by talking about what a reflex is, and why it thinks that the background needs to be white on all of that. I need to fix those things. But a reflex is a pre-programmed thing that happens. It's a pre-programmed neural circuit. Okay. And so what I'm doing here with the tendon tap is a reflex. The thing that really separates a reflex from an actual movement that may look the same is that the reflex does not need anything to happen from the brain. Okay. So when I do the tendon tap and I get knee extension from tendon tap, my motor cortex plays no role in that whatsoever. Okay. So I stretch the spindle signals to my motor neurons in the spinal cord, and then it goes right back down. And that's it. That's all that happens. There's no motor cortex involved whatsoever. Okay. The reason it does that is involving the motor cortex gives me an option to try to override it, and it takes longer. A lot of our reflexes are designed to remove something that is about to be really bad. Get away from the oven. Okay. You get a thing called the cross extensor reflex. You touch something hot, right? You flex and you extend on the other side and hold your balance. Okay. And so pull, and we do this. These are just simply reflexes. Or the flexor withdrawal. I call it the cross extensor, but it's the flexor withdrawal. You step on a Lego at 2 o'clock in the morning because your dogs are terrible and want to get up and be a pain in the ass, right? And your daughter won't put her Legos away. So you know how things are going at the Black household. And you step on one and you pull away. You flex to pull away from it, to withdraw, and you actually sort of extend on the other side and try to keep your balance. Okay. But it does not involve the brain. Now, with most reflexes, if I tell you this is coming, I can actively try to counteract the tendon tap. Okay. I do it a little bit by doing my hamstrings, but you can think your way through not activating those things. But most of the time, they're just these pre-programmed kind of simple short loops that we're going to have. Okay. I think that's really where I want to stop with all of these. Yeah.
Okay, we won't talk about the sympathetic and the parasympathetic nervous system yet. Okay, we'll save that for when we get into the cardiovascular side of things. Okay, we got 10 minutes. Here's what we're gonna do. Okay, 10 minutes. You guys were gracious enough to come to class. As soon as this will be funny, like we'll take like our second test and then we'll inevitably get like the first like marginally cold day. Or the marginally like cold and rainy day, and like people like when the class was today, like half the class wouldn't come. So, which is fine, but I'm gonna reward you guys for being here. Okay. So with the folks around you, I want you to write down if you said to your roommate, we are going to the gym today, and we are going to resistance train. We're going to lift weights. Write down what you would tell them you were going to do. Sets, reps, weights, what are you going to do?